So for our system, the thing we really need to define is the kinetic energy. And if we make the analogy, because we need to use this to define the Hamiltonian, and if we make an analogy to a linear system, the kinetic energy is equal to 1/2 mv squared, we can substitute this for angular kinetic energy. We can just substitute the definition, our equivalent to a mass is the moment of inertia, and the equivalent to velocity is the angular velocity. And so we can say the angular kinetic energy is 1/2 I omega squared. But we usually want to define this in terms of momentum. And so we'll switch that, right? We use this definition p squared over 2m, and we can switch that to now the angular momentum squared over 2I. All right, and so this is our rotational rotational kinetic energy. So just like for our linear systems, though, if we want this for quantum mechanics, we have to find what is this L squared operator, right? Just like when we switch this to the quantum kinetic energy, we need to use the momentum operator. And so that's sort of the next thing when you look at what is this L squared as an operator. Well, for the linear system, we ended up with this, del squared, right? For a three-dimensional system, we had negative h bar squared over 2m or mu if we're dealing with reduced masses. And that works fine for Cartesian coordinates where del squared gives you, right, d squared dx squared plus d squared dy squared plus d squared dz squared, right? And so, but in spherical coordinates, which are the natural coordinates for this system, we need to use a different definition of our second derivative here. So our three-dimensional second derivative, I'll write this out for you. The del squared operator for spherical coordinates is a little bit more complicated. It is 1 over r squared, first derivative with respect to r. I don't have this memorized. I'm looking up over at my notes over here. All right, r squared times the derivative with respect to r, where we keep theta and phi fixed, plus 1 over r squared sine theta times the derivative with respect to theta times sine theta derivative with respect to theta, where we keep r and phi fixed, plus there's a third term, 1 over r squared sine theta times the second derivative with respect to phi, where we keep r and theta fixed. So that whole thing, this comes from transforming our x, y, z coordinates. So taking this version of the del squared operator and transforming it to spherical coordinates, we get this beast down here. So these are completely equivalent to each other, but it seems pretty inconvenient in spherical coordinates. You may wonder why we bother with this mess of an equation here, but it is actually easier in spherical coordinates when the system is spherically symmetric, like the rigid rotator or hydrogen atom. All right, so we've defined this del squared operator, and one thing we can say for the rigid rotor is that r is fixed. So all of our changes in r, right, our dr terms, will go to 0. And so it does simplify this for this specific case where we have the rigid rotator. And so all those terms go to 0, and we can slightly simplify this. So our del squared operator, right, so h here will be equal to negative h bar squared, and we'll use, so this is for our rotation, negative h bar squared over 2i, right? So hold on, over 2 mu. We'll switch to I in just a second. And then we have all of this. So we get the terms that have ddr in them go to 0, but that still leaves a bunch of stuff. So 1 over r squared sine theta, dd theta, sine theta, dd theta at constant, won't worry about the constants, plus 1 over r squared sine theta, second derivative with respect to phi. Okay, and that's our Hamiltonian for the rigid rotor. And we can simplify this a little bit by changing some definitions. We can pull out all the r squareds. So these r squareds down here will combine with the mu here, and we can write this now in terms of the moment of inertia. So we'll get negative h bar squared over 2I. And then we'll define all this other stuff. Right, I'll just write this as del squared for theta and phi. And if and that represents all of this without the r squareds in the bottom, because those got factored out. And what we can do to somewhat simplify this is we can define the quantum angular momentum operator squared as all of the derivative part. Right, so we can define it as combined with the h bar squared. H bar squared times 1 over sine theta d theta sine theta d theta plus 1 over sine theta d squared d phi squared. And so h will be equal to negative, oh, sorry, not negative, because the negative is part of the L squared, but it's the angular momentum operator squared over 2I.